Good morning. Today we are going to look at section 4.4, which is the inferences for two population means still. But this time what we're looking at are what we call paired samples. So in the previous two notes, what we've done is we've looked at the individual independent samples. We've looked at the individual means of those samples, and we've compared them through a number of tests and developed our hypotheses as well. And what we're looking at today is we're looking at what we call the paired samples, where we can actually pair an individual from one sample set with an individual from another sample set and compare the differences between those two values, whatever they might be. And that'll kind of clear itself up a little bit here in our first example and then in subsequent examples from here on. But it kind of simplifies the process a little bit, but it only works when we have samples that can be paired together. If you think back to, I believe it was yesterday, we talked about the two different types of systems for the neurosurgery. One was dynamic and one was static. And in those two particular samples, we had more sample data for the dynamic than we did for the static. So we couldn't really pair those two up and make any claims based on what we're looking at today. So each test kind of has its own place. It just depends on what kind of data you have presented to you. And with this first example, we're just going to talk about how we can look at paired samples. And so we're talking about 5 married women and their 5 husbands. So you can see the females in the first column and the males in the second column. And for part A, we just simply want to list all possible paired samples of size 3. So that means we would draw 3 of those pairs out. So, for instance, Carla and Jim are linked for the purposes of this sample. That Carla can't be matched with Jeff, Mike, James, or Steve. Carla's only matched with Jim. So that is one pair. Kim, Joe, and Jeff is another pair, and so on. So I didn't delete this out of the notes because I didn't want to go through and rewrite all of it, just for the sake of brevity and to make sure that, I know you guys can look at this and understand. So this first, this chart that you see here is the answer to part A. It's the list of possible paired samples of size 3. So we have this first paired sample, Carla, Jim, Kim, Joe, and then Jamie and Mike, and then Carla, Jim, Kim, Joe, Teresa, James, Carla, Jim, Kim, Joe, Vicky, Steve, and we just did that methodically all the way down the list. And what we've generated are 10 samples. There are only 10 possible samples of size 3 out of those pairs. And what we find is that there is a 1 in 10 chance of selecting any one of those single samples. So that kind of gives you an idea of what we're talking about here with respect to the how the paired samples work. But what we're going to look at here in a little bit is what we want to do with the actual data, how we want to compare those means through just a single variable as opposed to using the means of whatever the first population is and the mean of the second population. And so with example 2, that's kind of where we come up with this process. So we're talking about a total different set of data here. We have the U.S. Census Bureau publishing information about the ages of married people. And suppose that we wanted to decide whether in the United States the mean age of married men differs. So we know then, since we're talking about differs, we're talking about a two-tailed test from the mean age of married women. Formulate the problem statistically by posing it as a hypothesis test. That's part A. Part B, explain the basic idea for carrying out the test. And then part C, suppose that 10 married couples in the U.S. are selected at random and that the ages and years of the people chosen are shown in the table. Discuss the use of these data to make a decision concerning the hypothesis test. So first we want to answer part A, which is just to simply formulate a hypothesis test. We have 2 different populations. We have the males and the females, or the husbands and wives. So we can let the husbands, that can be population 1, and the wives can be population 2. So the mean, or the means of the population that we're comparing would be mu sub 1, mu sub 2. And for the purposes of the hypothesis test, just like we've always done, first we state the null hypothesis, which is that the two means are equal to one another. And then the alternative hypothesis, as we've illustrated in the question itself, where it says that they differ, we know that this is a two-tailed test. So we're going to say that mu sub 1 is not equal to mu sub 2. So this is the foundation of our hypothesis test. And for the remainder of part B here, I'm not really going to write out a whole lot. I'm going to just discuss it. You can see it on the notes when I put up the completed set. But if we take random samples of 10 married women and 10 married men, and then we can apply a pooled t-test or a non-pooled t-test, which is what we've been doing. But in this case, because we can actually compare these men and women up, a paired sample test is actually more appropriate, and it's easier to conduct than using one of the previous two tests that we've looked at over the last couple of days. So here a pair would consist of each married couple, and by using a paired sample we're removing a lot of the variation that may exist. We've narrowed it down to this single variable, which is just the difference, and then you see right here we found the sum of the differences, and that comes into play a little bit later when we actually start to calculate the variables for the test statistics and do the hypothesis test. But it just simplifies the process a little bit when we can actually pair these two populations up and find just a difference that we can work with, as opposed to individual means of each population. So then for part C, we were asked to kind of just discuss what we would do with respect to the hypothesis test. And you can see, like I pointed out here, the last column indicates the differences between their ages. So we've subtracted the age of the wife from the age of the husband. That's why when you see these negative values, 21 minus 22 is negative 1, 33 minus 36 is negative 3, 54 minus 41 is 13. So we're subtracting the age of the wife from the age of the husband consistently down the list. And when we talk about this, if the null hypothesis is true, we would expect the paired differences to average roughly 0. And it doesn't have to be exactly 0. Approximately 0 is what we're really shooting for. If the average of all these differences in this fourth column is 0 or close to 0, then we can say that the null hypothesis is probably true. However, if that mean is too far away from 0, then chances are the null hypothesis is not true, and we would accept the alternative hypothesis. And then the way that we find that, we introduce, of course, a new variable, and this one is called d bar. And d bar is simply the sum of all the differences in that fourth column divided by the number of differences that exist. So we already have the sum is 36. We divide that by 10, and we get a difference, a mean difference of 3.6. So the question that we want to address through the hypothesis test is this difference of 3.6, can it be attributed to sampling error, or is that difference of 3.6 large enough to indicate that there is a difference in the means between males and female, or husbands and wives? And so to answer that question, we have to start talking about the distribution of the variable d bar. But for the purposes of example 2, this is as far as we needed to take it. We just needed to come up with how we're going to work with the variable, what variable we're going to be working with, and from here we're going to build upon that and come up with the remainder of this hypothesis test, and then consequently the confidence intervals as well. So what we were talking about here is called the paired t-statistic. And the paired t-statistic, it is typically normally distributed, and it does have a t-distribution with the degrees of freedom n minus 1. That's what we need to understand right now. First of all, is that it does have the degrees of freedom. Whatever the size is of the differences, the number of differences that exist, you just subtract 1 and you get your degrees of freedom. And we end up with this t statistic of d bar, which is the mean of all the differences, divided by the standard deviation of the differences, which is also then subsequently divided by the square root of the sample size. And we're going to apply all that here in a second to make more sense of it. So this is the paired t-test. This is something that we've seen this box many times over, and we kind of know what to look for in here, but it breaks down the purpose of the test, the assumptions of the test. We illustrate what the hypotheses are. The null hypothesis, the two means are equal. Then we have the two-tailed, left-tailed, and right-tailed test. We have a significance level of alpha. The variation on this test is our t statistic, which is going to be d bar, or the mean of the differences, divided by the sample standard deviation of the differences. And then we can then jump into the critical value approach, or the p-value approach. And one thing that I think I may have skipped over, type it in here. I'll add in how to find the standard deviation of the difference variable. So I need to type that in and add this to your notes. I apologize that it's not on here right now. I thought I had that. So when we look at example 2, we have a random sample of 10 married couples, and that gives the data on ages and years. It's shown in the second, third columns of the table. At the 5% significance level, do the data provide sufficient evidence to conclude that the mean age of married men differs from the mean age of married women? So we follow the same process. We do step 1, we state our null hypothesis. So step 1, from the box above, we state the null hypothesis and alternative, I should have said. So we have the null hypothesis is that the means are equal to one another. The alternative hypothesis is that the means of the two populations are not equal. And we know that this is a two-tailed test. We're going to have two boundary areas for the critical value approach that we would have rejection regions for. And we also have already computed d bar that was found in example 2. So we know that d bar is 3.6. It's the sum of the differences divided by 10, because we had 10 differences there. And this is the part that I did not type up in the notes, but it will be on your notes when you pull these up on the website. It's the standard deviation of the difference. And the standard deviation of the difference is the sum. Can't believe that. Sum of the differences squared minus sum of the differences squared yet again, but this time we divide those by n, which is our sample size, over n minus 1. So when we substitute in what we know from this example, the sum of all the differences is 352 after we square it, 36 squared. And then we also have 36 squared divided by 10. Over 10 minus 1, 9. And when we simplify this, we get that it is approximately 4.97. So there's our value for S sub D, which is our standard deviation of the differences. This allows us to compute our test statistic now, which is T is equal to D bar over S sub D divided by the square root of N. Substituting in what we know, D bar is 3.6, S sub D is 4.97, and the sample size is 10. Simplifying that, we get 2.291. So here's our test statistic that we want to compare in either our critical value or p-value approach. So for the critical value approach, we have degrees of freedom being n minus 1, which is going to be, in this case, 10 minus 1 is 9. So we have 9 degrees of freedom. And we have alpha equal to 0.05. So we're looking at a two-tailed test, so we know that that has to be plus minus T sub alpha over 2. It's going to be plus minus T sub 0.05 over 2, which will end up being plus minus T sub 0.025. And when we look at the T table at 0.025 with 9 degrees of freedom, we find that that's 2.262. And since this is a left or a two-tailed test, we use plus minus 2.262. And when we imagine that in the normal curve, here's positive 2.262, negative 2.262. Anything to the right of the positive value or left of the negative falls in the rejection region. And our test statistic is 2.291, which does fall into the rejection region. So we would reject the null hypothesis. Now, it's not a lot, but it's enough to put it into the rejection region. And that's why we use this, because we don't want to make just an assumption, oh, hey, 3.6 years is close enough to 0. We're going to assume that there's no difference in the means of the ages of the husbands versus the means of the ages of the wives. So that's why we use these tests, to kind of prevent human error. And then with the p-value approach, again, we're going to kind of do the same process that we've always done with the p-value approach. We know that the degrees of freedom is 9, and we know that our t-value that we're testing is 2.291. So when we go into the t-table, we look at degrees of freedom. We find where that value of 2.291 happens to fall. And then when we look up at the top of the table, we see that it is somewhere between 0.02 and 0.05. And our significance level is, actually in this case, happens to be 0.05. So we can see that P is less than 0.05. Therefore, we reject null hypothesis. And once we know how to do the test, the hypothesis test, we want to come up with the confidence interval so that we can, make a claim as to how confident we are in our result. And so the confidence intervals are found. We need to know the T sub alpha over 2. We need to know the degrees of freedom. And then so the endpoints of that confidence interval are found by using D bar plus or minus T sub alpha over 2 times the standard deviation of the difference divided by the square root of n. And we're going to use the same data from example 2 and 3 for example 4. We're going to use that age data in the second and third columns to obtain a 95% confidence interval for the differences between the mean ages of married men and the mean ages of married women. And so we know that since it's a 95% confidence interval, that gives us an alpha value of 0.05. And from the T table, I need to note that our degrees of freedom is 9. We see that T sub alpha over 2 9 degrees of freedom, T sub alpha 0.025 is going to be 2.262. So that gives us the values that we need to substitute into our endpoint equation that we just looked at above, and we're going to get 3.6 plus or minus 2.262 times 4.97. We've computed that standard deviation previously over the square root of 10, and what that simplifies to is 0.04 to 7.16. So what our claim is that we can be 95% confident that the mean age of married women, the mean age of married men exceeds the mean age of married women by somewhere between 0.04 years and 7.16 years. So with this test, we did find that there does exist a difference in the mean ages of married men versus married women, and we've also found a confidence interval with 95% confidence that mean difference is somewhere between 0.04 years and 7.16 years. The homework problems, there are a couple on here. What I would like for you guys to do is question number 2 and question number 4. They both relate to one another. So once you've done 2, 4 should be fairly straightforward as well. So that's it. This will be due on Friday by midnight. You guys are doing a pretty good job of getting everything in on time right now, and I appreciate that. And don't forget, tomorrow we will plan on having a Zoom class, probably around 2 o'clock. But for right now, again, if you have questions, you know how to reach me. Just send them to me, and I'll be happy to answer them. Hope everybody's doing well, and I'll be talking to you soon.